I work at the University of Cambridge between chemistry and physics departments. And I'm founded by Schlumberger Foundation. And today I will talk about cellulose nanocrystals. And this is very relevant to the summer school on liquid crystals. And I really want to thank the organizers for giving me the opportunity for presenting my work here. So cellulose is one of the most abundant materials on Earth. And unfortunately, it is not used for advanced materials. Everyone can hear me right? Yeah, okay. So it is not used for advanced applications so far because most of the time it is driven, the use of the material is driven by its cost, and cellulose is very cheap. And from higher scale here to wood and cotton, where you have a hierarchical structure, goes down to nanoscale, where you have individual nanofibrils and nanocrystals. It can offer, and we can source all different kinds of functionalities. And my basic research is taking something like this, a humble material, and turning into a nanophotonic structure like this. I'm just going to pass this on, and you will see the nice photonic iridescent films. So with everything, we get our inspiration from nature. And I was lucky enough to meet a brilliant scientist in Cambridge. She's called Silvia Vignolini, and she is working with plant sciences, and this is her finding that a fruit, a berry, Pollia condensata, has a structural color. So her basic research is finding the order and disorder in nature and relating to the color of the materials. So this was a really interesting finding because this berry acts like the origin of the color is coming from the beetles, the exact phenomenon with the beetles, the color with the beetles. The helicoidal ordering of the cellulose interacts with the visible wavelength of the electromagnetic radiation and reflects light. And each individual cell acts as a Bragg mirror. And this was a really nice finding because the animal kingdom and the plant kingdom find their own ways to assemble in a similar fashion to create similar structures, which relates to color eventually. So when Sylvia found out that I'm a chemist working on cellulose, her first question to me was, can you make this material for me in lab? And I will tell you how far we went. If you've seen the films, we are not too bad actually. So looking back to cellulose, how it is in nature, it forms this hierarchical macrofibrils, it goes into microfibrils, and there's this nanofibrils. And these nanofibrils, I'm showing it in very big form here, has crystalline bits. They are very stiff and strongly bonded, and it has this amorphous bits. And in chemistry department, this is our daily routine to extract the nanocrystalline bits from cellulose. And they have 100 to 300 nanometer in size and from 3 to 20 nanometer in diameter. And they have really high modulus. And the diameter and the length of the individual nanocrystals depend on how you extract the nanocrystals and also where you get the cellulose from. You can get cellulose from cotton, wood, or some bacteria produce cellulose, or some sea animals called tunicate produce cellulose as well. So once you produce the nanocrystals, I think so far being in the liquid crystalline school, you understand that the hero of the story is the nanocrystals, individual nanocrystals, because they have really high aspect ratios and they are very stiff. So they are ideal materials to make liquid crystals. And yes, they do. Upon slow evaporation, they form this twist. So the first layer of nanorods come together and form a layer, and the second layer comes and sits on top of it, and the third layer comes and sits on top of it. That's how they form the chiral pitch. And during slow evaporation, we are studying the dynamics. For days and days, they don't form anything. But once they are fully, very almost close to fully evaporation, they form these films with colors. And when you look at the electron microscope, you can see the oblique angle, the chiral pitch, but you can see some defects in the structure as well. And these are the first films. Let's take a closer look to our first films. You can see from blue to red, and in the middle, these edges are infrared, and in the middle, they have a different area, different section with green. You can't see it really well because it is very thin film, but it is not thin film interference, this is. So we have all these kind of different formations all around the Petri dish, which is not good for, if you're working with an optical physicist, they don't like that kind of structures. They want single colors, they don't want to work with that. So what can affect the liquid crystalline phase formation? Why we have all different colors of the different assemblies? The thing is, polydispersity is one of the key factors. So if you go to orangey bit, you have a pitch, chiral pitch, around 200. If you go to green bit here, we observed a pitch of 180 nanometer. And if we go to the blue, 160. Yeah, we have all different variations of the pitch, which is consistent with the theory. Yes, pitch is related to assembly of the materials. And we've also found out that all these particles are different from each other as well. So you can see the dispersion. The original material has high polydispersity, and by fractionation we can get the sizes narrowed down, which is a good thing. So all biologically originated materials, nanorods, tend to form this helical formation. And there are many theories to explain this phenomenon. So when a biological nanorod assembles itself, there's always a helical twist. So in case of DNA or viruses, it is easier to explain because they are already helical structures. So you can say they are transferring that kind of helical structure into the liquid crystalline phase formation. But in case of cellulose, we are producing a very random material. It is a very random nanorod. We are not very sure of what kind of structure the individual nanorods have. There are some theories, like the Orts group published. The electrostatic charges around the cellulose nanocrystals are helicoidal. So and they proven the concept to some extent, but not in all cases we see that. But that's that is something we are really thinking about and working on as well, because why the structure forms a helical twist, forming the chiral nematic phase, is something we really don't understand right now. Because in nature it is easier to relate, because cellulose and hemicellulose assemble together, and they are not in perfect crystallines. There's amorphous bits as well, so you have a larger polymer molecule. But now we are shortening it, and still it behaves the similar way. which is an interesting scientific question to work on. Well, I told you polydispersity is one of the major problems, but once you fractionate your sample and get a really narrow size distribution of particles, you can obtain single color films. And another thing is they have stronger color because they are assembling the same way. They are not, some of the parts are not assembling in different angles. It is nicely uniformly formed, which made us really, really happy actually. So where can you go from here? Well, once you made an iridescent film, it is nice to look at, yes, but where can you go from here? So this is essentially a photonic structure, and cellulose can be used as a template and for various things. One of the things is targeting photocatalysis, because when you make a structure for photocatalysis, if it is photonic structure, you slow down the waves at the end of the photonic band gap, so that improves the photocatalytic efficiency of the material, essentially. So this is what we are doing. We are using atomic layer deposition to replicate the cellulose kinematic phase, and we are forming this material. That's something we are still working on, and we're going to publish. So I'm not showing you all of the things, sorry, because there's loads to show, but I'm just giving you a glimpse of what we are doing. And we are carbonizing the cellulose and retaining the chironomatic order and putting gold on top of the structure, which would go to metamaterials, because the chiral nematic formation is a promising thing for metamaterials. And we are looking into different variations, the concentration, the ionic strength of the film, as I told you, polydispersity, and source of the cellulose, all the things. And we are putting into dynamics of the formation of the phases. And this is how the chironomatic carbon from chironomatic cellulose looks like. And this is something we are publishing soon as well. Oh, I shouldn't put my name, just my name, because I'm working with a really brilliant team right now, especially Sylvia and Hannah, just appeared here. We are all working together really well as a team. And if you have further questions or want to just do some collaboration with us, please write to me. And thanks for listening. And I can welcome some questions.
Question?
I'm sorry. I would like just to ask about the concentration of the nanocellulose in the evaporation films. It's 5%, right?
Yeah.
Don't the films become like fragile, or do you control very well the rate of evaporation?
The film you've seen is not that fragile. You need to break it. But the thing is, because of the high crystallinity of the material, it is about 90% crystalline. That's why it is brittle. It's not because of the film. But I think handling the film is not a problem. We can make other things with the film, and they are freestanding films, so there's no question about that.
Just because I tried with lower concentrations, and it was really fragile.
When you make very thin films,
yeah,
they don't lift up the substrate, and you can't handle them. Our films stick on the surface of the petri dish.
Yeah, we're using polystyrene.
Yeah.
Okay. Thank you.
Are the cellulose nanocrystals themselves chiral?
That's one of the questions we are looking at. I did some TEM, and there's a twist on the cellulose. So that might tell you some chirality. Oops. If it is something like that, yeah, might be like broad shaped chiral, right?
Because if they are, then this would be chiral phase ordering. Is that it?
Yeah, yeah, they need to be chiral. That's why we are questioning this a lot, because no one's seen many examples of the same solution, same nanorod. I can prove this. It is all chiral. It is something very interesting to look at, I think.
Great, thank you very much again.